Okay, in chapter 2, we kind of talk about the composition and structure of the atmosphere as it is now. Yes, you're going to see a few things mentioned about theories of how the atmosphere got here. I'll tell you flat out, I believe God created it in his own way, but he gave us some interesting curiosities that we like to look at. Why? How did it happen? So, all these are theories. None of these may be true. But right now, anyways, they're working theories. And I think God helps us to look at the weather and look at science with curiosity so that we can see his beautiful handiwork in all of this. So think of it that way this week as we talk about this weather and how the atmosphere developed, but also particular attention to how its composition and structure of the atmosphere. So the atmosphere is a whole. It covers the world. So in other words, what happens in the atmosphere in one part of the world impacts us. This is an example of that. There are dust, particularly in the summertime, that develops over the Saharas and then translates across the Atlantic Ocean. And you can see the cloud here in the satellite. It actually disrupts hurricanes. If we get these areas of dust moving across from there, it will actually destroy a hurricane. So it's something, again, impacts in the United States from dust over the Saharas. And with that, so let's talk about all kind of weather. Weather can go from tranquil, can be a beautiful day outside, and you just want to be out, to, I better not go out there, and you might even die if you're out in some of the weather that's out there. So the Earth is a system. It consists of the atmosphere, which is what we're going to talk about mostly, the hydrosphere, which is just water, like all the oceans, the geosphere. Think about volcanoes, landslides, motions of the continents, maybe. Biosphere, biological. Goes right in the name. Things like plants, like us. Atmosphere is really relatively thin. You think about it. Over half the mass of the atmosphere is in the first 18,000 feet. So what? Is that a little bit over 3 miles high? So, heck, you can walk 3 miles in a day with no trouble. Matter of fact, some people run it in an hour or less, way under an hour. So if you went in the vertical and could go upwards, you would find most of the atmosphere is very thin compared to the size of this globe that we call Earth. This is teeny tiny. But the atmosphere is, most of it where we are concerned with, is very uniform. It's a homosphere. What that means is that no matter whether you're on top of Mount Everest or down in a valley like Death Valley, you will find exactly the same percentages of atmospheric gases. Nitrogen will be 78, oxygen 20. However, the amount of air that is available to you is significantly different when you're down in the desert versus when you're high up in the mountains. But oxygen will always be that. Earth also has some aerosols in the atmosphere. Natural things, ocean spray, pollen, volcanic eruptions. We contribute to these by industrial waste. In our own way, we do agriculture. Water vapor. By volume, it's less than 4%, and it's almost all of it's in the lowest 1 kilometer of the atmosphere. Yeah, you look outside, you don't know if it's going to rain or not. So at 4%, wow, that's a big influence on the weather. Carbon dioxide, required for life. We need it for photosynthesis. Sometimes too much of a good thing can be bad, but we do require it. Pollution. I can remember growing up when pollution was really bad. And I mean in the sense that I could go out to Pittsburgh I lived in Pennsylvania at the time, and we would go out there sometimes or down to Philadelphia, and you could not see it at all. And it was all because of pollution. When I had my first job in West Virginia, in Charleston, West Virginia, there was always pollution down in the valleys. All of that has gotten a lot better over the years. We've improved our quality of living by dealing with some of this pollution. And the way we study the atmosphere, the way we study anything in the science, is what we call the scientific methods. So I want to give you an example. One of the issues I dealt with the Weather Service at Wakefield, Virginia, was how did we forecast when thunderstorms were going to move across the Appalachian Mountains and continue to intensify as they moved east across Virginia. It was something we got wrong way too often. Many times we would say, oh, these are going to die, and they did not. Other times we would say, oh man, this is going to strengthen, and they didn't. They died. So it was a question we observed, a problem. We formed some hypotheses, some things to look at, maybe why this happens. So we worked on developing tests as to what might be working and what might not. We went back and looked at past cases of weather. We went through these hypotheses again, reformulated them, and finally we have come up with some methods now where we can get about a 95% chance that we know whether those thunderstorms are going to continue to move east or whether they're going to die. So our forecast has gotten a lot better in that particular area. So that's how you apply the scientific method to this. Places like Purdue, there's a tornado vortex chamber which simulates tornadoes, gives us a physical representation of them. Mathematical models, that was my field when I was working on my grad degree, and I like to play with them even when I was in the field writing forecast. I worked on what they call the mesoscale model, and I developed some information about how fluxes of temperature changed and impacted very tiny resolution things such as a sea breeze. We observe the weather. The better observations we have, the better the weather forecast is going to be. One of the tools we observed is ASOS. ASOS, almost every airport have one. Why does an airport have that? Well, they have it very simply because airplanes need to know the weather before they take off and land. They could be coming into some really bad situations otherwise. This is a safety measure for the aircraft. And by having it there, the Weather Service got information. And that's 24 hours a day, every day. And literally the observations are taken every second. So you can actually look at data that's continuous. There's a cooperative network out there where volunteers literally look at the temperatures, precipitation over the course of a day. Some of those volunteers provide that information comes back to the Weather Service so we can develop max-min climatologies. We get a better idea of how droughts are progressing because we're getting it monthly or even every few days. Then you have the real volunteer network, COCORAS, which is all volunteers that reports things like rain, hail, snow. You're all welcome to become members of that. Radiosondes, all they are is a big balloon that expands as it goes up and eventually bursts. Attached to that balloon is an instrument called a radiosonde. That instrument records temperature, pressure, humidity, and because of the direction of the motion of the balloon, which is controlled by the wind, we actually can get the wind speed and direction as well. And it's done throughout a vertical layer of the atmosphere. You can see there's a small instrument that's attached to it. There's actually a parachute on that instrument, so when the balloon breaks, the parachute lets it come back down, and if we get lucky enough to refine it, we can save a few bucks, refurbish it, and reuse it again. Not often do we get that lucky. Dropsondes, very similar instrument. They're just dropped from the top, so they come down. Instead of going up with the balloon, they're dropped into a hurricane, for example. I showed you pictures on the video 1 of a tornado and how it looked on radar. So remote sensing is basically looking out at something that isn't close to you. It's remote. So with the radar, I can look out 120 miles in any direction, basically. Satellites, I can cover the globe. All these are remote sensing. And here you can see the temperature profile in the atmosphere and how it goes. So we live in the troposphere. All weather occurs in the troposphere. Notice the temperature decreases with height. If you ever climb a mountain, it's going to get colder and colder the higher you get. That is part of the troposphere. Now, if you were in the stratosphere, it's going to start getting warmer. Mesosphere starts getting colder. Thermosphere starts getting warmer. So you notice we've transitioned each layer of the atmosphere by how the temperature profile goes. Finally, auroras are just found in the ionosphere. They're caused by the solar wind, which is electromagnetic particles that come out from the sun. The more that come out, the stronger that auroras will be, the better chance and the bigger area they'll cover. And then we had one the other week that got very big and actually came down into the United States pretty far. So that was based all on the solar winds. So hope you get a little bit out of this. Let me know again if you have any questions.